Greetings everybody. Let's have a more in-depth look at our eigenvalues and eigenvectors with a computational example. So let's say that we are given the matrix A that has the entries 2, 2, 3, 1, 2, 1, 2, negative 2, 1. Then kind of the first step in finding the eigenvalues is we need to calculate the characteristic polynomial. So the characteristic polynomial from the last video is just the determinant of A minus lambda times the identity element. Well, that gives us a matrix of the form 2 minus lambda, 2 minus lambda, 1 minus lambda. Then if we look at the determinant of that, using the cofactor expansion, we get an expression that has this form to it. Now, if we just take that thing, distribute all of the values, kind of combine like terms, blah, 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 simplify it out, then we end up with an expression like this. So the determinant of A minus lambda I is P of lambda. It looks like minus lambda cubed plus 5 lambda squared minus 2 lambda minus 8. Well, if we take that thing and we graph it with whatever our favorite graphing application is, then we see that we're going to have roots for that thing at negative 1, we're going to have a root at 2, and we're going to have a root at 4 for that thing. So it's going to factor as minus lambda plus 1 times lambda minus 2 times lambda minus 4. And so our eigenvalues then just become negative 1, 2, and 4. Now, the collection of all of our eigenvalues is can also be called the spectrum of A. So the set of all of our eigenvalues, so the spectrum of A in this case, negative 1, 2, and 4. So if we then take lambda equal to negative 1, so our first eigenvalue, we take that thing and we plug it in for lambda, then we get a matrix that is of the form 3, 2, 3, 1, 3, 1, 2, negative 1, 2. So then what we want to do is really find the kernel of this thing. So that's going to be our corresponding eigenspace. So if we transform this thing to reduced row echelon form, if we're going to keep track of all our values, just if you're playing along at home, the matrix M, so M times A minus lambda I, so M times this matrix, gives us our reduced row echelon form of 1, 0, 1, 0, 1, 0, 0, 0, 0 along the bottom. And we know that we're going to get a row of zeros on the bottom because our eigenvalue that we chose is a root of our characteristic polynomial. The root of our characteristic polynomial guarantees that our determinant is going to be 0, which guarantees that we've got a non-trivial solution, which is the same thing as a 0 row showing up down in reduced row echelon form. And so if we look at the kernel of that expression, then we get a vector that looks like minus alpha, 0, alpha, for alpha being any real number. And so this thing is really just spanned by one vector itself, negative 1, 0, 1. It's kind of one typical example that we could use as kind of a generator for, or as a basis for our particular kernel. And so the eigenspace corresponding to lambda is equal to negative 1 is just the span of negative 1, 0, 1. We can go back and actually check that, yes, does this really give us what we're supposed to have? We go back to our original matrix, 2, 2, 3, 1, 2, 1, 2, negative 2, 1. We multiply that by our vector negative 1, 0, 1, gives us a 1, 0, negative 1. Well, if we factor a negative 1 out of that, then we get our original vector back. So we've got our eigenvalue, we've got our eigenvector, and so we've got our eigenspace, and this one, sure enough, actually does work in that case. So we can go about doing the exact same thing for our eigenvalues for lambda is equal to 2 and lambda equal to 4. So for lambda is equal to 2, we get an eigenspace, which is just going to be the span of negative 2, 3, 2. If we look at the eigenspace corresponding to 4, that gives us the span of 8, 5, 2 for that vector. And so kind of our first step in really looking at these eigenspaces in a little more depth, if we have two different eigenspaces, so E1 and E2 are eigenspaces of A corresponding to lambda sub 1 and lambda sub 2 respectively, with lambda sub 1 not equal to lambda sub 2, so these are different eigenspaces, then the intersection of those, the only vectors that they actually have in common, is the 0 vector. So what does the proof look like for that? Well, we imagine that we've got a vector in E1 intersect E2. Well, what that means is that lambda of x is equal to lambda sub 1 of x, and a times x is equal to lambda 2 times x. Well, since these guys are equal, it then means that lambda 1x minus lambda 2x is also going to be equal. So if we subtract those, we get lambda 1 minus lambda 2 times x being 0. And since lambda sub 1 is not equal to lambda sub 2, we can divide by that. So canceling out our scalar just gives us x is equal to 0. And so the only vector that we have that's common to two separate eigenspaces is going to be the 0 vector. Okay, now we can actually do a little bit better than that. Instead of just having trivial intersections, we can do kind of go one step further and make those orthogonal. And for that, you'll have to wait for the next video, and I will see you guys there.